5 to the negative 2. 5 times itself negative 2. Just think how that sounds. 5 times itself negative 2 times. That doesn't make any sense. So you're supposed to do something first with a negative 2 power. Right here, rule number 8. A negative exponent will mean reciprocal. So the first thing you're going to do is you're going to flip it. If it's in the numerator, you flip it down to the denominator. If it's in the denominator, it's got to be under something. It's under 1. 1 over a to the n. If it's in the denominator, you flip it up. If you flip it up, it would be over a 1, but anything over 1 is just so. So the first thing you do with 5 to the negative 2, reciprocal. 1 over 5 to the positive 2, and 5 squared is 25. 1 over 25. You follow that? Yeah.
You want to read the negative to the.
When I flip it up or flip it down, it becomes a positive. If I carry the negative with it, you mean like negative 25? But the 5 was never negative. I wouldn't change the sign. I wouldn't be multiplying negative 5. It was never a negative number. The only thing that negative 2 up here does, it is reciprocal. Once it flips down, it's a positive exponent. It never changes the sign of the base. It never changes the sign of the base at all. The only way I can change a positive 25 into a negative 25, I would have to multiply by a negative 1. I have to multiply by a negative 1. That's the only way to change the sign of something. And I'm not multiplying by anything. I'm just flipping. $36.5. 36 times itself a half a time. Not 36 times 1/2, because I will see a lot of 18s on this. But it's not 36 times 1/2, unless you don't write it correctly. You will lose points if you don't write it correctly. It's an exponent, but I will see you with 36.5. That's not 36.5. I'm in a quadrant when I grade tests like this. That's why I got to point this out. When I grade tests like this, I don't know if you mean 36.5, 36 times a half, or 36 to the half. When you leave something that looks like that, because that's not a power. A power is a superscript. The base to a power. So the power has to be a little smaller in the top right-hand corner, superscript. Otherwise, I can't tell. When you look at your test, some of you are going to think it's times 1/2. But the whole chapter is exponents. So why would it be times 1/2 if we're doing exponents? Which means if you're not sure, come up and ask. Don't guess. Just come up and ask. Is that a times 1/2? Is that a times 2? Is that a times negative 2? Don't guess, ask. And then if you ask, I can make sure you know, and then you know that you're going to be able to do it. That is the key. If you leave that as an answer, then I would do too big. Usually -1. Because again, it's not an exponent. Spelling counts. Spelling should count all the time. Especially these days, you have spell check. Everything is correcting everything for us now. Which is kind of sad because now we don't pay attention to anything that we do because somebody's going to correct it for us. The machine. And that's not a good thing. I've seen Terminator a lot of times.
It's happening now.
Yeah. Stephen Hawking, who Stephen Hawking was. Check out the movie The Theory of Everything. Okay, with Eddie Redmayne. Okay, Stephen Hawking, was diagnosed with Lou Gehrig's disease in 1967. He was given 2 years to live. He passed away in 2017 or 2018, I believe. He's a cosmologist, not a cosmetologist, but a cosmologist who's looking for the theory, the unification theory that describes one math equation to describe how everything has happened. Quantum mechanics basically united with gravitational theory. Einstein stuff. He was considered to be one of the smartest people in the world, but he's also one that was confined to a wheelchair, wasn't able to speak. He was hooked up to a computer, and he would use eye movements, or sometimes when he could still find some small motor movements, was able to move the mouse to highlight sentences that he would say. And he had that computer voice. Okay. Well, as far as people on the planet, but trapped in a body that didn't work. He couldn't even breathe for himself. He ended up also, getting married 3 times once he contracted the disease because he kept cheating on his wife. Einstein married his cousin. So, yeah, they're kind of going. And he married her because he said she made good sausages.
Was it Tesla another decision?
Possibly. Was it Tesla that tried? Who electrocuted the horse or the elephant? Was that Edison or Tesla? Was Edison to prove that Tesla was dangerous? I think. Yeah. That will come up.
Everything else married his cousin.
Could it? Well, yeah, when she was 14.
Yeah.
We're such an evolved species. Yeah, yes.
That's what most genius people just married their cousins all the time.
I don't know. I don't really know. Well, I mean, it wasn't illegal. His first wife was a physicist as well. And she did a lot of the calculations and math for him. Because he wouldn't want to be bothered with all the minutia. He was into the theory and the thought theory, coming up with the experiments and what if. But then to do the math, it was like, okay, just don't want to fiddle with that. I want to focus on the experimentation.
Let's really just
Minutia.
define that.
The details, all the little putting the pieces together. Now he does, but the calculations that kind of take us there, he goes through that, he understands that, but he doesn't want to sit down and do it. He was a CD student. I've seen, documentaries where they show the report cards. He wasn't a great student because he didn't want to sit down and do the work. My son is really smart, but he's also a lazy student. He never studied for his SATs. And he scored higher than all his friends, and they're all AP geniuses. And he only took it once. Back then it was out of 2,400. I think he scored 2180 something. And it's like, you're an ass. He never passed an AP calculus prep test. And the night before, when I was trying to help him, he has a migraine. I'm going, good luck tomorrow. And he ends up passing with a 4. It's like, all right, you take tests really well, but you don't do homework and you don't want to go to class. You don't want to wait for the morning. So that's going to be hard to do. When he actually quit college and dropped out, and he had to get a job, and he had to be on the job at 6 a.m. Because working, you didn't have to take homework with. You didn't do any work at home. There was nothing when the job was done at the end of the day. And that's what he hated his job after 8 years. So then he's now a vet tech, which he gets to play with dogs or help dogs all the time. And he's really good at it. So, which, he's happy. He's a better father than I ever was, and probably I'm sure he's a better husband than I ever was, or that I am. But anyway. His wife is straight A ever since kindergarten through her master's degree. So they offset each other really well. Well, I remember going to a movie, his wife, well, his girlfriend had, her, the whole family, and she has her computer before the movie started. Computer's open, studying for her final the next day, and she has like over 100% of the class. And it's like, what are you doing? You're going to be fine. Not times a half to that. So out of all these, it's an exponent. So it's here. 1/2, 1/2 is the nth root of that base. So if the denominator is always the root you're going to take. So if that's a 2, it's a square root. Now, when you convert this, you rewrite it. You don't put a 2 in that knot. When it's a 2, it's just a square root. Now, if you want to put a 2, that's fine. But I'm telling you, you're never going to see anything else ever put a 2. When you just see the radical sign, it's just a square root. We're looking for a 2 of a kind.
What, in the end, like the whole picture here, what is the point of simplifying it from 36.5? Like, where would you apply that?
Well, I want to take the square root of something.
Oh, okay.
Yeah. So if I have x squared, here's the reason. X squared, where we just came from, equals 25. So we have to undo the square, and we want to get, what's the answer? So we didn't do this in the last chapter. Why did we take the square root? How did it become a square root? What? We just went, we said square root undoes the square. We're trying to solve for x, for x. So what that means is, if we want x equals what, then what we want is x to the first. To get x by itself, we need x to the first power. To get x to the first, I have to undo that power of 2. Now, dividing by 2 does not undo that because it's not a multiplication problem. It's an exponent. So dividing both sides by 2 doesn't work. So somehow I have to undo that 2 up here. So what we do, because this is all that was there. This is all that they had to work with, was exponent rules. Is you would have to raise this to get a 1. You would raise this side to the 1/2 power. If I raise the left side to the 1/2, I got to raise the right side to the 1/2. And so what does that mean? That means that over here, rule number 2, power to a power, you multiply. So this is x to the 2 times 1/2. And over here we have 25 to the 1/2. And 2 times 1/2 is x to the 2/2. 2/2 is 1. That's how we get x to the first. That's how we know the 1/2 of each side, power of the 1/2, is going to undo that x squared and give us x. Now we just have to figure out what the heck does this mean. Over here, we're looking at what times what is 25. Well, 5 times 5. We know the answer. But how do we undo the power? What is going to be our rule to undo this? What operation? What are we going to call it? And so eventually, what's the quicker way to do instead of powers? Because the notation starts getting really messy. Especially when students' handwriting is so bad. We change it to the radical sign.
I mean, so I guess I'm there over probably in some tutorials. So before, for example, we were solving equations. Now we're finding the equation to solve.
No. We're still solving equations when we have. But the only way to undo exponents were other exponents.
Okay.
So we can only undo powers with other exponents.
So
The rules of
I'm
everything.
doing it.
Yeah. So basically, this was everything.
Yeah.
So when we undid a power of 2, we had to use exponents to undo the exponent. So all that happened was this x to the 1/2 became square root instead of a 1/2 power. We don't write it, we convert it.
So it's just a simplified version of trying to break that down.
So,
Thank you.
so the boils down to is language. This is the exponential form, that's the radical form. They're the same thing. They mean you're going to do the same thing. So sometimes it's easier to work with something as an exponent. Sometimes it's better to work with something as a radical. In calculus, if you're okay there, and you want to take, don't worry about what this is. If I want to take the derivative with respect to x of x square root x, we don't have a rule for this. We have a rule for the derivative with respect to x of x to the 3/2. That is x to the 3/2. Okay? And the derivative would equal 3/2 times x to the 1/2. Again, don't worry about what I just did. But I got x to the 3/2 because of exponent rules. X square root x is x times, this is x to the what? What's the exponent right here? 1/2. And when we multiply, rule number 1, when I multiply the same base, I add the powers. So this is x, what's the exponent here of x? 1. So this is x to the 1 plus 1/2. So this is 1 plus 1/2 is 3/2. That's how I converted this into this. Now I can use what's called the power rule. When I take the derivative of the power, I use the power rule. All these rules for, you have the power rule, you have the chain rule, you have the quotient rule, you have the product rule. You have a, oh my gosh. I already said, actually said chain rule, you got all the trig rules, you got the inverse trig rules, you got the logarithm rules, you got the exponent rules. There's 24 basic differentiation. You know how you have to memorize certain rules to be like these or 10? In calculus, you have 24 basic differentiation and then 20 basic integration. So you have 44. And if you don't know them by heart, then you can't do the work. You have to be able to add and the bases are the same, power to a power. If you don't have that first step done, it doesn't work because you can't make it up. All right. So this is just square root 36. I understand this. This is not going to make sense to me nearly as much. Well, what's square root 36? 6. 36 to the half is 6. What is square? You have a calculator, so you should have like, what? 400. Did you need a calculator? No. About 20 to the third. But I'm multiplying by 3. 8,000. What about 20 to the, shouldn't have to, be 20 to the fifth. Well, if I go from 3 is 8,000 and I skip 4. $32,000. I went from 400 to 1,000. 3,000,000. $200,000. Now here's why. 20 is 2 times 10, isn't it? Yes. Okay. To the fifth. Rule number 3. A times B to the n. So when you have a product to a power, each factor is raised to the individual power. I raise A to the n times B to the n. So I can do 2 to the fifth times 10 to the fifth. So 2 to the fifth is 32. You should know your powers of 2. Remember the chart of powers. And 10 to the fifth is the 1 with 5 zeros. 5. So it's 32/100,000, which means it's a 32 with 5 zeros. That's all. Or you can look at it and go, all right, 2 to the fifth, 32, and then 10 to the fifth, I'm going to have 5 zeros. 32 and 10 to 5 zeros. So if I had 30 to the third, what's 3 to the third? Another one you should already know by heart. 3 to the third is. 3 times 3 times 3 is 27. And then how many zeros? 3 zeros. 27,000. Okay. That's why in the chart of powers, obviously it listed 1 all the way across. I listed 2 all the way to the power of 10. The more powers of 2 you know, the better off you're going to be, especially here in chapter 4. I listed 3 all the way to the 10, but you really should go at least 3 to the 6. And you will be able to use calculators. But the more you just know and recognize, again, it's like recognizing the factors of 56. 56, 7 times 8. 56, 4 times 14. Okay. Powers of 4. Powers of 4 are related to the powers of 2 because 4 is 2 times 2. Powers of 5. This one. 5 to the 4th is 625. That's going to happen a lot. Powers of 6. 6 to the 3rd is 216. That's going to happen a lot. Probably maybe a 6 to the 4th. 7, 8, 9. 9 to the 3rd, 729. So look at the powers of 10. Because every time you raise it to a power, you just put 1 more zero. But right here, 10 to the 0. Look at this column. All the answers are what? The power of 0. They're all 1s. Because a 10 would be a 1 with 0 zeros. Because everything to the 0 power, rule number 7 is 1, except 0. So a 10 to the 0 is a 1 with no zeros, a 1. But 10 to the first is just 10, 1 0. 10 squared is 100, a 1 with 2 zeros. 10 to the 10th would be a 1 with 10 zeros. But I also put on the list it's 20 to the 10th. Because 20 to the 10th is 2 to the 10th and then 10 zeros. 2 to the 10th is 1024 and then 10 zeros. Okay. Just to see the pattern. And that's what it's about. Math is about. So math has been described as the science of pattern. There's patterns in everything. Okay. All right. A fraction. Okay, right here, number 4. A over B to a power is the numerator and denominator both raised to that same power. It's just like the product to a power. A product to a power, each factor gets a power. A fraction to the power, the numerator and denominator both get the power. So this one is rewritten as 64 to the 1/2 over 49 to the 1/2. And the 1/2 power is a square root. Square root of 64 over square root of 49. And the square root of 64 is 8. And the square root of 49 is 7. It's predicated on translate. I don't know what the heck I'm doing when I look at 64 over 49 to the 1/2. So what else does that mean? What does it mean when I raise something to the 1/2? 1/2 is a square root. Rewrite it. If what you're looking at doesn't make sense, if what you're looking at can't be done, this is what you use to rewrite it. Change it into what can be done. $125 to the 2/3. One thing about Stephen Hawking when he was still lecturing, but he couldn't speak so people could understand. He had teaching assistants who understood his mumblings. So he would mumble, and then his teaching assistant would write whatever he was mumbling. That's what happened. Somebody could write, transfer. So let's go. 125 to the 2/3 is 25. Now, not because I'm looking at it, because I'm translating it and then I'm doing the problem. 125 to the 2/3 power. So it's not 1 over 2. The numerator is now something different other than a 1. So now instead of rule 9, it's rule 10. So here's rule 10. Rule 10 has 2 options. How do you know which one? I'll pick one and see. Well, which one should I pick? No, I don't know. Eeny, meeny, miny, moe. Well, what was that going to do? Itsy bitsy spot? I don't know. Easy thing to do. Pick one. Close your eyes and point. Flip a coin. You just got to pick one though. You can't stare at it. That's not going to do it. The denominator is always the radical. It's the index. It's the root you're going to take. So it's right here, the nth root. The numerator now is the power of the base. A to the n power. So that's how you can rewrite it. The denominator is always the radical that we're going to take, the nth root. It was the same as number 9, 1 over n. It was the square root or cube root, whatever. Or a to the m over n. Still an nth root of a, but you raise it to the m power after you finish the root. So you either raise it to the power, then take the root, or you take the root, then raise it to the power. And the only way to know which one is which is to practice. And maybe you'll start to see it. And maybe you fill in the powers in that chart at any time, so you start to recognize which way to go. So this one, the denominator is a 3, so it's a cube root. The base is 125, so that's the radicand. The numerator is a 2, so that's a power. So it's a cube root of 125 squared, if I use this first one. 4. The denominator is a 3, so it's a cube root of 125. That's the base, so that's the radicand. And then I'm going to square it after I take the cube root. Either one. I didn't do this in my head yesterday. I don't think I can do it today either. So here's the thing. This is the cube root of 15,625. When I square it. Okay. So now you got to break it out of cube root jail. To break it out of cube root jail, we need 3 of a kind. So give me 2 numbers that go into, because we factor tree, break it apart with 2. Give me 2 numbers that go into 15,625. You know it ends in a 5, so you can take, divide by 5. But the nice thing about things that end in 25s, if it ends in a 25, 25 goes into it. If it ends in 2 zeros, 25 goes into it. If it ends in a 50, 25 will go into it. If it ends in a 75, 25 goes into it. Think about it. 25 goes into 100, 125, 150, 175. 25 goes into anything with a quarter value. So give me 2 numbers that go into 15,625.
31.25.
What's that?
31.25.
30 times what?
Times 5.
That's not, so you want to use 5 and 3,125. So now you've got to bring the 5 down. And what's going to go into this? So 5 times 625?
Yeah.
So I have, got to make sure you bring all the branches down. And then what's going to make 625?
125.
So 5 times 125. So here's these. And then what's going to make that?
25.
5 times, should keep going to doing 5.
Yeah.
5 times 25, okay.
I'm on a roll.
So now we have 5 and a 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 5. Which is absolutely fine. Just make sure your branches come all the way down to the bottom. Because you don't want to leave any 5s behind. And we're looking for 3 of a kind. So 3 3s make a run for it. 1 5 breaks out and lives. These 3 5s make a run for it. Only 1 5 breaks out and lives. On the outside, if they multiply back together, the answer is 25. Fine. Now, you can pick whatever you want to pick. Well, let's think about where we just came from, how we got 15,625. it was the cube root of 125 squared, right? From here. Right? Yes. That was the problem. We converted it to this, and then we made this. You know what you could have factored with? 125 times 125. Because we just came from there. And 125, if you recognize it, you know how I told you that when you do the 8, it's from now on, it's going to be 2 times 2 times 2? Instead of going 2 times 4 and then 2 times, and you get 2 times 2. Okay. 125, 5 times 5 times 5, because it's 5 to the third. On your exponent table, and 5 to the third. 5 to the 5 account. A 125 is 5 to the third. I told you about 5 going across so many. 625. 25 times 25. Know that one. Okay, it helps. It's not a race. Do what you need to do to get the right answer. It's not a race. You don't get extra points for turning it in, or you need to turn it in by 11 or 11:50, but you don't get points for like, I'm done in 10 minutes. But try this now. You can write it like this, which means you're going to break apart a huge number. Or I take the cube root first, and then I'm going to square the answer. Because now I'm taking the cube root of a much smaller number. This is 25 times 5. So you have a 5 times 5 and a 5. It's a cube root. I need 3 of a kind. So those 3 5s make a run for it. 1 5 makes it out. Now that 5 that made it out is still inside the parentheses that I have to square. So now 5 squared, 25. So you need to think about it in 2 different ways. Which one do you think is going to be simpler? Sometimes the one on the left, sometimes the one on the right. Six. First thing you have to do is what? The very first thing. It's right in front of you, just say it. Just like the problem number 1. What was the first thing we had to do with the first question? When you read it, whether out loud and you mumble it or in your head, 9 to the negative 3 over 2. How do we do 9 times itself negative 3 over 2 times? The first word that comes in that you spout out, 9 to the negative, that doesn't make any sense. 3 over 2 is going to be one of the, that's the next thing you got to deal with. But 9 to the net, I don't raise things to negative powers. You only raise things to positive powers. So what are you supposed to do? If you're going to make a difference with your ability in mathematics, you have to speak up and engage. You cannot passively wait. Because right now I know the answer is bouncing around in a lot of your heads. The more you communicate it, the better student you're going to be at this. Because you have to build your confidence. The first thing you see is that negative exponent. What happens with a negative exponent? Flip it here. You flip it. We don't raise things to negative powers. We need positive powers. So rule number 8, we have a negative power, you flip it down. So this is now going to be 1 over 9 to the positive 3 over 2. First thing. And then we don't raise anything to a fraction. We convert it into a radical. So a 3 over 2 power. So this is 1 over. The denominator's a 2, so it's a square root. The base is a 9, so the 9 is the radicand. Now I'm either going to take the square root of 9 and I'm going to cube it first, or I'm going to go 1 over the square root of 9 and I'll cube the answer after I take the square root. Okay? Which of those, this first one or that second one, which one looks like the better choice? If you think it through, if I raise 9 to the third, it becomes a bigger number. Then I got to figure out its square root, break it down. Or I'm taking the square root of 9, and then I'm just going to raise it to the third power. Out of those two possibilities, you got to make a choice. Am I going to turn left or right? Am I going to go one on the right, one on the, or the one on the left? First one or second one? Second one. Second one. Because the square root of 9 is just 3. So this is just 1 over 3 to the third. And 3 to the third is 27. 1 over 27. Now, this one, 9 to the third, just trust me, is the square root of 729. Now you got to figure out the square root of 729. So then you got to start breaking it down. How about you use 3 9s? So then you have 3, another 3, and another 3. So a 3 escapes, another 3 escapes, and another 3 escapes. 3 times 3 times 3 is 27. But now you better remember it's 1 over the 27. Because that 27 is in the denominator. But which one was the easier way to go? You're going to know is, hey, I've done these before. I've set these up before. Going over here. 1 over 1,000 to a negative 2/3. So what happens there? First thing about that negative exponent, what are you going to do? You're going to flip it up. This one goes up. So now it's just 1,000 to a positive 2/3. Negative exponent means reciprocal. We're going to flip it. So now we write it as a radical. The denominator is a 3, so it's a cube root. Now I want to point something out. The cube root, that 3 has to be inside that little notch. Because if you write it like this, or even like this, that looks like 3 times the square root. If it's a cube root, it's written like that. That's the spelling of a cube root. Don't matter. So it's a cube root of 1,000. And I can either, and I'm not gonna write it out twice, but just watch. I can either square this first, and think about it, if I square this first, it's gonna get huge, and then we gotta find groups of 3. Or I can take the cube root and square it afterwards. Which way do you want to go? Cube root it and then square it, or square it first? After or before? After. And that's only because this is already a nice perfect cube. 1,000, 3 zeros. So this is 10 times 10 times 10. It's 10 to the third. And if you're not sure, this is 10 times 100, which is 10. 100 is 10 times 10. So at 10 escapes, and it's still got to be squared. And the answer is 100. So 1 over 1,000 to the negative 2/3 is equal to 100.
What was the way that you put it before when you just moved?
I put it like this, I put cube root of 1,000, and you can square it before you take the cube root, which makes this a big number, and then I gotta find groups of 3 afterwards. So why make it huge when you have a nice number that simplifies, and then you can find the equivalent? And it's just a matter of perspective. Some problems are going to be done differently. But practicing will give you a better option. So you at least know how to set it up either way. If you don't set it up either way, you won't have an idea of what you do.
Really quick on number 6, where it says, when you flip it and it goes from 9 to 3 over 2, and then you break everything down, where does the 2 go?
The 2 is the square root. We don't put 2.
So the bottom 2 is just that.
It's, yeah, with a square root, we never put a 2.
Okay, so it's same, okay.
Yeah.
Linking things.
Okay. Now I'm going to show you something interesting. Twenty to the 4/3. So this is how we would normally do it. You got a cube root, and you either do 20 to the 4th, or you do the cube root, and you do 20, and you raise it to the 4th. Look at both of those. Which one would be the best way? I'll tell you right now, there's only one way. The first one. Because the second one, 20 is not a perfect cube. I can't, there's no 3 of a kind when I do this 20. 20 is 4 times 5. There's no perfect cubes in a 20. So then I just have to raise it to the 4th and, well, whatever. But if I do this, and again, don't multiply this out. Don't go to 160,000. This is just 20 times of 20 times of 20 times of 20. Hey, there's 3 20s. So 120 survives and breaks out. There's a 20 left behind in the cube root. 20 cube root 20. To the 4/3. 4/3. 4/3. 4/3. 4/3. 4/3. How many times can 4? Let me go into 4 even. Once. What's the remainder? 1/3. 1 and 1/3. How many 20s escaped? 1. How many 20s went back into jail? One escaped, one went back in the cube root, 1 1/3. It's a mixed number. It's an improper fraction. And all it is 3 goes into 4 once. So 1 whole 20 will escape. There's a remainder of 1 back into the cube root jail. So when you have an improper fraction as your power, you can look at it from the mixed number perspective. When we did, I erased it, but it was 2/3. There's something to the 2/3. I don't know. I think about 1,000 to the 2/3. 3 doesn't go into 2 even, so I can't do that process. So that's proper fraction. But when it's improper, 20 to the 8/3. 8/3. How many times can 3 go into 28 even? 2 times, what's the remainder? 2. So 8 and 2/3. So this is going to be 2 20s escapes. Now, when I say 2 20s, 20 squared escapes, 20 times 20 escapes. And then the cube root of 20 squared is going to be stuck in there. Okay. So you have a 400 cube root 400. Improper fraction. You treat them like a mixed number. The whole number escapes. The remainder goes back in that cube in that jail. All right, we're back at 10.